Hello class, today we'll be covering energy. That'll be our unit for today. So if we think of types of energy, there's many different kinds. There's kinetic, which is the energy of motion. There's potential. Today we'll be specifically talking about gravitational potential energy. This is just the energy due to a gravitational position, like a bowling ball on a shelf, or a ball on a cliff, or a skateboarder on the top of a hill. There's chemical energy, electrostatic, nuclear, and thermal and light. We won't be discussing those in too much detail in this unit. There's ways to transition between types of energy. You can take potential energy, specifically gravitational potential energy, and turn it into kinetic by just simply pushing a ball off of a shelf. The potential energy stored in that ball when it was placed high up off the ground turned into kinetic energy as the force of gravity pulled that ball down. So if we have a ball on a shelf, simply pushing this ball off the shelf will cause the ball to fall. And as it falls, its potential energy up here will turn into kinetic energy at the bottom. A few more transitions just to talk about. A bowling ball being pushed off of a cliff, again, that's just what we talked about. That is potential energy becoming kinetic energy. A Nerf gun firing a dart, well, we can picture a little Nerf gun firing a dart this way. Nerf guns have little springs in them that, as you cock the part on the top back, compresses the spring, so you have a spring potential energy that when you pull the trigger releases, turning into kinetic energy of the dart being fired. Eating food and going for a run. So food is chemical energy that your body can absorb, and if you're going for a run, you are moving, so that is kinetic energy. So that is chemical to kinetic energy. A wind turbine. So this is fun. If we have a wind turbine, we have a long shaft and blades. And as the wind runs into those blades, we will see some rotation about those blades. These blades turn a bar, which turn a generator, which produce electricity. So we have kinetic energy in the wind becoming kinetic energy in the wind, becoming kinetic energy in the blade's motion, becoming electrical energy once the blades spin the generator. Gasoline-powered generator is chemical energy in gasoline, becoming mechanical energy in the engine it is turning on and powering, turning into electrical energy once that generator is spinning and producing a current. An atomic bomb is nuclear energy, becoming a lot of heat, a lot of light, and a lot of kinetic. A glow stick would simply be chemical energy. Once you crack that glow stick and it starts glowing, becoming light. So, we don't have to cover this entire slide, but the ones I want to focus on are the types of potential energy gravitational. So what variables play into this? Well, if we think of our ball on a cliff example, it'd be a lot easier to get that ball on the cliff if it was a ping pong ball relative to if it was a bowling ball. If it was a bowling ball, it'd be much harder because its mass is heavier. So we know mass is a variable. We know it's hard to lift things on planet Earth relative to, say, the moon, so we know that gravity is a variable, and it's easier to put a bowling ball on a 1 meter high desk than a 10 meter high desk, so we know height is a variable as well. Playing into this, we know the gravitational potential energies equation is simply mass times gravity times height. Spring, chemical, and nuclear, we can go into the equations in a later video, but for this unit, we're just going to focus on gravitational potential. Kinetic energy, the energy of motion. If we have a person throwing a ball. That ball has kinetic energy because it is moving. We see the variables here in kinetic energy is 1/2 mv squared, which just means it is the mass of the object times the velocity of the object squared. Mass, remember, is in kilograms, and velocity is in meters per second. So we have some examples here. We know in a heavy ball versus a light ball going the same speed, we know that the heavy ball has more mass and therefore will have higher kinetic energy. The light ball will have less. A fast ball and a slow ball, if they're the same mass, the fast ball will have more kinetic energy because it is going faster at a higher velocity. A fast light ball versus a slow heavy ball, we don't know. Maybe the mass is enough to compensate, maybe the velocity. We're going to do an example problem. It's a fun one. Would you rather get hit with a comet or an asteroid? So comets have an average mass of 5e14 kilos, which is just 5 followed by 14 zeros, and a speed of 70 kilometers a second, or 70,000 meters per second. A large asteroid in the asteroid belt is 5e15 kilos, and it travels 18,000 meters per second. So there's a hard and an easy way to do this. If we were to just do the numbers, we can find out that the kinetic energy of the comet is equal to 1/2 the mass of the comet, which is 5e14, times its velocity 70,000 squared, which is equal to, pulling out a calculator, that is equal to 1.225 E24 joules of kinetic energy. Doing the same math for the asteroid, we see 1/2 its mass, which is 5e15 kilograms, times its speed of 18,000 meters per second squared. Again, using our calculator. We see that this is equal to 8.1 E23 joules. So we know that the comet has more kinetic energy as this number is larger than this number. That was one way of solving it. However, there is a second one. We see here that the asteroid is 10 times heavier mass-wise than the comet. However, it is about 4 times slower. 18 is about 1/4 of 70 with some generous rounding. So we have 10 times the mass, but we see in the equation up here that velocity is squared. What this means is we take our 4 times higher velocity in our comet and we can square it, and we see that 16 is larger than 10. This means conceptually you can just do in your head that the comet will have more kinetic energy as its velocity more than makes up for its lack in mass. So this is just what we're covering here, a few steps to show the math. We did this lab in class. If we're seeing it for the first time, we're seeing that kinetic energy, velocity on the y-axis, and kinetic energy on the x-axis. If we were to calculate kinetic energy for a few points, we know when the velocity is 0, the kinetic energy is 0, as there is no motion. And we know at its top speed, it has some sort of high velocity and kinetic energy, right here, 117 meters per second. But if we were to start filling in points on this graph, we would notice that it's not a straight line, but more of a logarithmic shape. This is because kinetic energy increases with the square of velocity in our equation 1/2 mv squared. We can see that this is actual data taken velocity versus time, as time is constant force, as the energy from the engine is its maximum constant output. But we can go the other way too. We can go from potential to kinetic energy. So again, let's say we have a bowling ball and it's sitting on a cliff. What kind of energy does it have at this point? Well, it's not moving. So if we look at 1/2 mv squared for kinetic energy, we see that velocity is 0, and therefore there's no kinetic energy if it's just sitting at the top. If we look at gravitational potential energy, however, we know mgh, again that's mass times the gravitational constant times the height. Well, it has a mass, it's a bowling ball. It's on Earth, so there's gravity, and it is off the ground, so there is height. Therefore, it has some potential energy. If it were to fall off of this cliff, and it were to be right above the bottom of this cliff, right before it hits the ground, it would have almost no potential energy because this height variable would be close to 0. Where did that energy go? Energy cannot be created or destroyed in this unit. So it means the potential energy at the top of the hill was all converted to kinetic energy. We're going to ignore friction for now. What that means is gravity pulled it down, increasing the velocity as it went. This did not happen all at once. This was gradual over the course of the fall. We can picture that if we picture the ball halfway down the fall. It still has half its height to go, therefore it has half its potential energy. However, if it's falling at this point, it's not stationary here, it is moving. And if it's moving, it has some kinetic energy. This means half of the potential energy has become kinetic energy, and half is still in potential energy, despite the fact that this ball is moving. Yes, energy cannot be created or destroyed. So if a bowling ball is 10 meters off the ground, we can draw this, a bowling ball 10 meters off the ground. How fast is it right before it hits the ground? A lot of people would say that mass matters here, but what we see here is we have potential energy becoming kinetic energy, and we notice that both sides have mass, so we're able to cancel them out. The question here is how fast is it, the bowling ball, right before it hits the ground? So we can solve for v squared over here. This should be v to the power of 2. So to solve for that, we can simply multiply this side by 2 to take care of this half right here, and multiply this side by 2 to even it out. So at this point we're at 2gh is equal to v squared. Remember, we canceled mass out of both sides. And then to solve for this, we can just take the square root of both sides, and this gives us v is the square root of 2gh. As you can see, mass is not a variable here. We can think of this in the experiments where we can drop a golf ball and a bowling ball from the same height at the same time. They'll hit the ground at the same time. On Earth, on the Moon, this was carried out with a feather and a hammer. They'll hit the ground at the same time with the same speed. The only thing is, due to kinetic energy being 1/2 mv squared, the heavier object, because it has the same speed, will have more kinetic energy as the mass is greater. Here's just another way of solving that. We see this is 2gh to the power of 1/2. This must be an error in loading it into this app. So here's another example problem, just taking it to the next level. This was a weapon designed to be in space. It was a large tungsten rod of 11,000 kilograms, and it was placed at a certain height in space to where when it was going to hit the ground, it would be going 10 times the speed of sound. The speed of sound is 343 meters per second, so 10 times that would simply be 3430 meters per second. So if we do this and we see how many joules of energy, how much kinetic energy would one rod have just prior to reaching the surface of the Earth, we know that Ke is equal to 1/2 mv squared. We know it has how many joules of energy? Well, we don't know its velocity. We do know its velocity. Its velocity is 3430 meters per second squared. And we know its mass times 11,000 kilograms times 1/2 is equal to its kinetic energy. Putting this in our calculator, we see that it has about 6.47 e to the 10th joules of kinetic energy just before it hits the ground. However, kinetic energy can also become potential energy. If we have a Nerf gun on the ground and fire it straight up, we know it will reach a height. What kind of energy does the dart have the second it's fired? Well, it's barely off the ground, so we're going to assume potential energy is 0, but it has a velocity, so it has a kinetic energy. Does the dart have a velocity when it's fired? Yes, it does. And if we think of the dart being fired straight up, it will eventually come straight down. We can define this upward velocity as the positive velocity, and this downward velocity as the negative velocity. If any number, if this is a simple xy graph with positive numbers and negative numbers, if the velocity started positive and ended negative, this means right in the middle it had to hit 0. This will happen at the peak of the dart's path. At the peak of the dart's path, the velocity will be essentially 0. If the velocity is essentially 0, we know it has no kinetic energy. But it started with kinetic energy. So where did it go? Energy cannot be created or destroyed. It became potential energy at the very top. If no kinetic energy was at the top, where did the energy go? Into potential energy. How high did it go? We can simply cross out mass on both sides, divide by g on both sides. Again, this should be v squared and v squared. And we see h is simply equal to 1/2 v squared over g. Notice that mass is not a variable here. Any mass launched straight up at the same speed will reach the same height, ignoring friction. Just some things to think about to check in. If the bowling ball on the cliff was twice the mass, would it affect how long it took to hit the ground? No. Just like the hammer and feather on the moon dropped, or a golf ball and a bowling ball dropped. Any masses dropped from the same height at the same time, ignoring friction, will hit the ground at the same time at the same speed. If the dart was twice the mass but fired at the same speed, would it reach the same height? Yes, it would. Again, we see here that we can solve for the height of the dart, and mass is not a variable. If the ball was dropped from twice the height, would it be going faster or slower before it hit the ground? So, I'm perfectly comfortable jumping off a little 1-foot curb, but I'm not perfectly comfortable jumping off a 10-foot curb, because I'll be going much faster when I hit the ground, and my ankles will hurt quite a bit more, because there's more kinetic energy in my body as it leaves the ground, and as it hits it again. So, if a ball is dropped from twice the height, it will be going significantly faster than a ball dropped from half the height before it hits the ground. If the dart was fired slower, would it reach as high? Again, no, because we can see here that height depends on the velocity. So, why does this matter? Bullet fired versus bullet dropped. If a bullet is fired perfectly horizontal at the exact same time as an identical bullet is being dropped, if these bullets are from the same height, which hits the ground first? They actually hit the ground at the same time. Because if they're from the same height, if we're only looking at the y-axis, that's the up and down axis, the force of gravity affects both of these things at the same time. So, if this one took 3 seconds to fall, this one will take 3 seconds to fall. However, if we know this one took 3 seconds to fall, let's say it was going 10 meters per second. We knew it had 10 meters per second in the x direction and 3 seconds to go. The x direction, ignoring friction, the x velocity will never change. So if it is going 10 meters per second in the x direction over the course of 3 seconds, we know that 10 times 3 is 30. So this bullet will travel 30 meters before it hits the ground. 30. Yes, they travel the same time. So, now that we know they hit the ground at the same time, we can know how far the bullets went, as we solved in the previous slides. So if we're going to do a practice problem, a ball is rolling towards a cliff at a speed of 5 meters per second. How far does the ball travel before hitting the ground at the first point of contact? If the cliff is 50 meters tall, this gives us some things to work with. For ball on cliff problems, we need to find the velocity of the y final first. This will give us our delta v in the y direction. This will allow us to solve for time, which allows us to solve for the displacement in the x direction. So a ball being dropped at the very peak, we can think of this as a ball being launched straight upwards, reaching the peak, and coming back down. At this peak, right as it's coming off the cliff, the Vy initial is 0. But we know right before it hits the ground, this is not the case. It has some velocity in the y direction, as gravity has been affecting it over its entire drop. So how do we find that? We know that, solved earlier, the velocity in the y direction is simply 2 times g times h. Using our calculators, we can solve that the Vy final, using 9.81 as our gravitational constant, is equal to 31.32 meters per second. If we know the y velocity started at 0 and ended at 31.32 meters per second, we know the change is also 31.32 meters per second. So how do we solve for time? There's another equation. Delta v is equal to a times t, which means the change in velocity is equal to the acceleration in that axis times the time. Our delta v again was 31.32 meters per second. Our acceleration is 9.81 meters over seconds squared times time. So to solve for this, we just divide our delta v by our gravitational constant 9.81. Doing this on our calculator, we find that the time in the air was 3.19 seconds. If we know it's in the air for 3.19 seconds, the only thing we have to look for at this point, and for the first time, is the x velocity of 5 meters per second. 5 meters per second times our 3.19 seconds gives us an x displacement of 15.96 meters. What this means is that this ball traveled 15.96 meters in this direction before it hit the ground. Here are some steps. Feel free to pause the video and take some notes. Moving on. Force or velocity at an angle can be split into parts. So, if a ball is no longer being launched just off a cliff or straight up, but at an angle, we can split this motion into its x and y components. To do this is very simple. We can define the hypotenuse of this right triangle we're drawing. The hypotenuse would be this gray arrow. We can define the hypotenuse as the overall speed. The ball is traveling 10 meters per second, so we know that the hypotenuse is 10 meters per second. 30 degrees above the horizontal, that's referring to this angle right here. This is 30 degrees. Remember that sine of any angle is equal to the opposite over hypotenuse. Cos of any angle is equal to the adjacent over the hypotenuse, referring to sides. The opposite of this side refers to the y component. Remember, this is up and down, y-axis. The adjacent of this angle refers to the bottom angle, the x component. So if this is overall velocity, this is velocity in the y direction and velocity in the x direction. So if we were to solve for this, sine of 30 is equal to approximately 0.5, exactly actually. Cos of 30 is equal to 0.866. And all we have to do as both of these numbers are being divided by their hypotenuse, is just multiply these numbers by the hypotenuse to find our Vy and our Vx, respectively. So if we multiply 0.5 times 10, we'll find that the Vy is equal to 5 meters per second. And our Vx, once we multiply that by 10, is 8.66. A way to check this is look at the angle, 30 degrees. That is mainly horizontal. If it was close to 89, 85, anything above 45 degrees, we would know that the y velocity should be larger. However, 30 degrees is closer to horizontal than it is vertical, which makes sense because 8.66 meters per second is larger than 5 meters per second. Here are some steps showing how to solve for the y direction. Feel free to pause the video and take some notes. Here's my steps for the x direction. Again, feel free to pause the video and take some notes. So what if the ball was launched upwards? Well, we can talk about it. A ball thrown has two axes of motion, a y direction and an x direction, but the force is only in the y direction, because once that ball leaves my hand, the only force applied to it is the force of gravity, which always acts straight down. If a force is being applied in one axis, how does that impact the object's motion? Well, we know a ball being thrown at some angle has an x velocity, a y velocity, and a total velocity. We know this x velocity is never going to change over the entire course of the flight. Its y velocity will change as it's being impacted by gravity, which means only the y-axis experiences some force. If we know an object's initial y velocity, we know its final y velocity. If a ball was launched up at 5 meters per second, it will come down at 5 meters per second. If the y component is 5 meters per second of a ball being launched at an angle, the y component of the ball as it reaches the same plane will be 5 meters per second as well. But remember, it's coming down, so it's negative. 5 meters per second minus negative 5 meters per second gives us our delta velocity. 5 meters per second minus a negative, we simply distribute the negative. 5 minus negative 5 becomes a plus, 5 plus 5. Our change in velocity is simply 10 meters per second. Once we find our delta velocity, we can simply divide by our gravitational acceleration 9.81 to find the time. And then once we know time, we can use the x velocity to see how far that ball goes once it was launched. This is an experiment we ran in class. We had the professor as well as a student both throw an object. The student's x velocity was much higher, but his object landed about 1 meter, while the professor's landed about 10 meters. But I thought x velocity was the only thing that mattered if launched from the same height. This does not, because on Earth we have drag. The object I was throwing was a tennis ball, and the object the student was throwing was an unfolded tissue. Any motion, picture a box on a table moving in this direction, will eventually slow down to a stop, which means some force had to be acting opposite its plane of motion. This force is friction. Friction in the air is air resistance, or drag, as this object has to move air particles out of the way as it carries on its motion. This is the reason parachutes are able to save people's lives. The faster you're moving, as you continue to fall, the force of gravity does not change upon you. However, the force of drag does. Terminal velocity is reached when the force of drag is equal to the force of gravity. This does not mean you stop falling, but it means your velocity is no longer existent. It is equal to 0. This doesn't make a lot of sense in the y direction. Let's think about it in the x direction. If this is me and I'm being pulled by two ropes, I have one person pulling me to the left and one person pulling me to the right. We can say, if they're pulling on the same way, I will not be moved left or right. I will not be accelerated in the left or right direction. We can do this in the y direction as well. If I have 882 newtons pulling me up and 882 newtons pulling me down, I have no net force. Therefore, I'm not accelerating. What about work? Work is simply a force times a distance. What this means is if I push one box 1 meter with a force of 5 newtons, I have accomplished 5 joules of work. However, work needs a direction as well. If a train is sitting on its tracks and I try and push it off its tracks, no matter how hard I push, I probably won't move it off the tracks. Which means in this axis, the axis perpendicular to the train's plane of axis of motion, it did not move in this axis. Therefore, the distance is 0, and as work is equal to force times distance, if distance is 0, work has to be 0, regardless of how hard I push that train. This applies if the train is moving as well. As we recall, the axis of motion is this direction. However, the axis of my force is this axis. In this axis, the train experiences no motion. So again, work is force times distance. Distance is 0, and therefore work is 0. Work is simply a force times a distance. Something to consider: what is keeping a 100 kilogram weight on the ground? As we all know, gravity likes to keep things on the ground. This does not mean there are 100 newtons. However, force is equal to mass times acceleration, which means force, keeping this box on the ground, is equal to its mass of 100 kilograms times the gravitational acceleration constant of 9.81. This means there are 981 newtons of force keeping it on the ground. If I were to lift this box at all, I would need a hair over 981 newtons to make the net force in the upward direction. However, in physics, we mostly ignore these zeros and just say it takes 981 newtons to lift the box. If how much work is done when we lift this 2 meters, recall that work is equal to force times distance. We found our force is 981 newtons, and our distance is 2 meters. Therefore, we accomplish 1982 joules of work. However, what did we just do? Force is simply a mass times an acceleration. And work is force times distance, which means work is mass times acceleration times distance. If we were to do this again, mass times acceleration, we can write that as g. Distance, since we're lifting it, we can write this as height. Here we see mass times gravity times height. This is equal to our potential energy equation, which is also in joules. This is something where we don't have to ignore friction now. Solving the same problem as last time, if we have 10 kilograms lifted 25 meters in the air on Earth, we see we did 2,452.5 joules of work. If we were to unfold that parachute, if that parachute were to go from a tight bundle to a long parachute and quickly lift it up, it would take more work. The reason being right here. We have the same force of gravity in either example. In the first example, we have a force of gravity that we have to overcome with the force of lifting. The force of drag is relatively small, as there's not a lot of air resistance, as the surface area is very small. However, in the second example, we have the same force of gravity, but a larger force of resistance, as the surface area is much larger and it is being quickly lifted. Therefore, the force of lifting must be larger to compensate for this. As work is equal to force times distance, if we have to up the force over the same distance, we have to up the work. This applies to track as well, track and training. You will see sprinters running with resistance parachutes. This simply increases your frontal area, therefore increasing the drag, increasing the work you have to do to reach the same speed. If I were to run an 8-minute mile on a track without a parachute, I would expect a longer time using a parachute and actually a shorter time in a treadmill. On a treadmill, although you are working and are moving, you are not moving relative to the air around you. Therefore, you are not displacing air particles and not experiencing drag. Here are some force diagrams demonstrating this point. Why does this matter? In class, we brought up Kipchoge, who recently ran a 2-hour marathon, and we had a debate if, due to his pacers, along with other factors such as shoes, flat track, ideal conditions, if the drag the pacers displaced for Kipchoge invalidates his 2-hour marathon time. This is not a debate class, but many opinions were voiced. Thank you for coming to my lecture. That concludes our Unit 1 topic on energy.